Good day, everyone. My name is Arnaud Huck, and I'll present you today a webinar on the OpendTect Geo-Body interpretation. I'll start with doing some basic attribute analysis within OpendTect, because in order to be able to interpret geobodies, we'll see that you will need to prepare the necessary input for the interpretation and the creation of the geobodies. And as a result, soon after this basic attribute analysis, I'll already be in a position to pick very simple complex bodies, which is the first kind of bodies you can interpret in OpendTect. After picking the simple convex geobodies, I'll show you how you can interpret geobodies using polygons, a combination of polygons and horizons. And then we'll move on into a more complex set of geobodies extracted using either implicit representation or using the Voxel connectivity filter that is used to assess the connectivity, volumetric connectivity between different parts of geobodies. And finally, the last kind of geobodies we'll see today is coming from interconnected amplitude bodies from multiple volumes, from multiple realizations using the MPSI volumetrics. Finally, I'll conclude this webinar by showing you how you can save and export geobodies outside OpendTect. The format of the webinar will be pretty much a live demonstration of these capabilities in the OpendTect software. Let me start by this example. I'll work today in all my exercises on the F3 demo dataset from the Dutch North Sea in a rather shallow interval around 1 second TVT. The interpretation will be guided by these two horizons that I'm loading right now in the scene that will represent the top and the base of the interval of interest for the extraction of the geobodies. You can see that these two horizons are pretty close to each other. They represent a rather small interval, and in order to assess the time difference, the very first thing I'll do is actually, and that is part of the interpretation, is that I'll compute the isopac between the top and the base horizon, and the output will be displayed as a grid on the top horizon, which is this one. So it sees on this isopac map the time difference between the two horizons that is roughly around here to 14, 20, up to 40 milliseconds. Now, in order to start the attribute analysis, there are basic attributes you can try to display on your data. We provide as a starting point default attribute sets that can be utilized in each and every survey in order to start with screening through various attributes on your data set. The sets that I've used today that I've already sub-selected is one similarity attribute that compares laterally how similar the trace segments are looking alike. And so the trace segments are defined by their time gate, their positioning, and the positioning is corrected by making use of the full steering, so the local dip of the seismic events. A second attribute that is very often of much use when screening through the data set at a very early stage is the instantaneous amplitude attribute. And finally, we'll see how this spectral decomposition tool can be used in order to interpret our seismic data set. Now, let me first apply the similarity attribute on this horizon. Similarity was computed beforehand and has now been restored as a surface data. And what we can see, and that we could already see a bit before on on the isopack map is that this dataset is split in two with a major fault offsetting the data that I'm highlighting here with mouse pointer. And in the northeastern part of the data, we see lots of low similarities that are linked to the presence of sand ridges. There are also features anomalies on the northwestern part of the survey in the same azimuth, but they are corresponding to actually downlapping features on the dataset. Finally, in the southwestern part, we see here a number of deep marine channels meandering throughout the survey. And that is what we can say by making a quick look on this similarity attribute. Now, if I'm loading, once I've loaded the similarity, the instantaneous amplitude attribute, we can see that there is a pretty high amplitude response in the eastern part on a very narrow band that is going from the southeast to the northwest, and the entire second part of the survey, the western part of the survey, is also featuring high amplitudes. For this geo-body extraction exercises, I'll focus on the western part, and in order to focus very clearly on this part, I have picked a polygon in order to really delimit the area in which we'll do the interpretation. Now, as I said earlier when presenting the webinar, the very first kind of bodies you can pick are very simple convex geobodies. In order to work and to create these geobodies, I'll actually not work along horizon because they need to be along a plane surface, so either an inline, a cross line, or a time slice. So that's why I'm loading now the instantaneous amplitude along that time slice. And the creation of such a simple body can be made by making a right-click in the body element of the scene and using the option to create a new polygon body. Then the picking can be done just like any other pick set or polygon in OpendTect by making a number of seeds that will delimit the interval of the polygon. Seeds are fully editable, and so we can steer the creation of this body in the way we want it. But still, it is what we call a convex body because it's rather difficult to bring it very concave. It is somewhat possible, but there'll be some influences on the other sides of the area. And this work that has been done now on time slice, on one single time slice, has to be repeated on another time slice. So this is a time slice underneath. I'm now switching to a base view of the survey, looking down. And actually, one can pick the polygon by making discrete seeds, or you can keep the mouse clicked, and that will draw a continuous line that you see here. And as you see, as it goes concave, we can get in troubles. But this is delimiting the polygon. And as you can see, the polygon grows in 3D as it is being picked. Now, if I move to to another time slice, this time I'll go shallower than the previous one. I can keep on picking this polygon as needed up to how the attribute is thought to be responding. Now, if I remove this time slice, we see the body that is created in 3 dimensions, and that is only the result of the very various peaks that have been made, that are visualized here with the yellow cubes. And this is the most simple kind of body you can create in OpendTect. The main problem with such a body is actually that it will not follow the structure at all, because it has to be interpreted on sections. And one way to overcome this is to use a second kind of bodies that are created using polygons and horizons. Actually, the polygons will be picked in the very same manner as what I just did, but the one main difference is that they can be picked. Now, if I create a new polygon here in the polygon element in the tree, that will be the contour of the anomaly. And I'll choose a relevant color to say it very clearly on top of the existing. Well, that was already an existing name. And now I can try to pick this object as I can see it from this attribute. Now, the instantaneous attribute is an attribute that is potentially very useful. But actually, there are a number of other interpretation techniques that you can use that can hopefully provide a sharper overview of this anomaly. One of them is to apply a quick UVQ, which is a waveform segmentation that would be run around on the target interval within this UVQ contour area. What it will do, it will actually load the seismic data in a very small waveform, here -8 to +28 milliseconds, relative to this top horizon. And it will try to cluster all the existing waveforms from the seismic volume into 6 very distinct classes that are themselves the output of this training. Now, I'll also provide the contour polygon to limit this classification to only the eastern part of the survey. Now that the data has been extracted, the neural network is actually training, and once we have reached a satisfying match, we can stop the training, and OpendTect will apply directly after this, after the training was completed, the neural network to this horizon. And the neural network results in 2 grids: a match grid, which is a quality control, that should most often not be below 80%, and a class grid, that is a number of integers, here 1 to 6, displayed on this top interpretation. But in order to see what this integer means, actually we need to go into the neural network report and display the waveforms that are the class centers of this neural network training. And you can see that I can very easily put the same colors on top of the corresponding waveforms, and that will actually tell me what is the waveform that corresponds to a given class center. So for instance, the blue color, which seems to match pretty well with our high amplitude anomaly, is the class center number 1, and this class center features a very bright amplitude slightly underneath the top interpretation, which is at 0, and also a very bright trough below that important peak. So, and what we can say is that all these seismic traces alongside this blue pattern have about the same shape as this class center. That is how you can interpret. That is how you can interpret the UVQ segmentation. From this UVQ, you can actually see that we can refine the polygon, and we can pick our polygon a bit more accurately if we are to interpret this blue feature. So we can, because we see that it has a much more complicated shape, we can actually highlight this shape by drawing a line where we see the UVQ map to go from one segment to another one. And as I said, the picking can be done either in the usual way, I would say, by making seeds at various positions, or by drawing lines, and that is one of the new features you have, and it comes from the adaptation we have done for picking on digitizing screens, where you can digitize these screens. And that allows you to get a much more accurate picking of the lateral contour of this geobody. Now, it still requires some time, so I've made already an outline for this UVQ map, well, actually for a previous one. And now what you can do is you can go in the right-click menu of your polygon and you can create a body from this polygon using one horizon as the top of the horizon of the body and one horizon as the base of the geobody. And because we are using horizons to constrain vertically the body, we'll always get in this manner a body that is following the seismic structure, because it is truncated vertically by two horizons, and laterally it is truncated by the lateral extent of the picked polygon. You see, you can see this geobody, this new geobody in 3D. So it follows, of course, very accurately the polygon that we can now dismiss from the view. And these bodies are not only very nice display features, they are actual objects on which you can do your analysis and go a bit further, because not only, you see, it's not only one single layer here in the tree, you have a sub-menu that allows you to apply attributes on the geobody itself, so on the outer part of the geobody. And that allows you, for instance, to go a bit further and to visualize how the amplitude is changing within the picked facies that was originating previously from the UVQ map. So as you can see, we are still within the same body, but there are distinct changes in amplitudes within that body. If you need to apply several attributes, actually you can very quickly reload a second time the same body in the scene, and that will allow you, once it is loaded, to apply a different attribute. And for instance, what I would like to show you now is that we'll apply the similarity attribute on this second copy of the polygon-based picked sand body. And the similarity is something we'll try to analyze jointly with the instantaneous amplitude as extracted from the geobody. I need to apply the relevant color bar, set the properties of the geobody, because that influences the look and feel of the attribute. And if you want to toggle very easily between the two attributes, so the two geobodies, let me remind you, you have this option in the graphics toolbar that allows you to display the current element only. When it is on, like now, you will see only the highlighted element in the tree, and you can switch between the two with the keyboard arrows up and down. So that allows you to very quickly, you can change the camera position, go somewhere else, and then go back and forth into various attributes. So not only you see the body amplitude on the top at the top and base of the geobody, but you have it available on all the various sides and camera positions you can imagine. So this is a simple geobody. The two types that I've presented now, so simple convex bodies and the ones interpreted using polygons and horizons, are more or less manually drawn by the interpreter. And as a result, you get all the freedom with these bodies to do whatever you want. Now, the other three types of geobodies that we'll see now differ in a way that will not be exactly picked, hand-picked by the interpreter, but they will be extracted from the amplitudes of a given volume instead. The one way to extract a geobody from amplitudes of a volume is called implicit representation. How does it work? Well, instead of having this geobody that is here, I need to toggle off the display single element only. Instead of picking on an horizon or a time slice, what we'll do, we'll add a volume element in the tree, and this will give us the usual volume probe that we can move around, and it will center on the anomaly we would like to analyze. Okay, so it's a 3D, small 3D cube in which we will load the attribute instantaneous amplitude. And that will make available all the amplitudes of the volume within that cube. And if we change the display type to volume rendering with a color by like chimney that has partial transparency, then the combination of all these visualization features allow us to see only the large amplitudes within this 3D cube. So we're looking at now in blue and in yellow only the largest instantaneous amplitude within that 3D cube. Now, there is one problem that's very evident to see, is that the response is not limited to the interval of interest, and that is because the volume probe is a cube, so it cannot follow the horizon. In order to overcome this, there is an easy way to arrange that. We can process the attribute in batch, not using the standard attribute option, but using the option to process it between horizons or along one single horizon. So if we choose to output this attribute between horizons, we'll have to choose the input attribute, the top horizon and the base horizon, and we may want to offset, let's say, by 12 milliseconds above the top horizon down to 8 milliseconds below the base horizon. And the most important part to do here, and that is why we'll be able to trim out all the areas around it, we will output the undefined value outside the interval defined by the top surface and the offset and the bottom surface and the offset. And we'll output this in a new cube which will contain the same instantaneous amplitude attribute, but only in this very small interval. Once the batch processing is finished, we can reload the attribute by selecting it in this very same volume probe and applying it again. So that will refresh the content of the volumetric probe with the new attribute, and this time there's no doubt that the output response will be limited to the interval of interest, and will be 100% sure that there will be nothing outside the interval of interest. So this is already half of the work that needs to be done when choosing the path of creating job bodies using implicit representation. So we have to load the data in the volume viewer, and once the data is loaded in the volume viewer, regardless of actually any color bar setting, we can go in the Add menu and use the option to create an ISO surface. The ISO surface will compute for one given value, that is an amplitude of the input volume. It will compute the envelope that separates the lowest amplitudes from the largest amplitudes with respect to this cutoff value. So the cutoff can be adjusted here and either updated or you can press on OK. And once the ISO surface is computed, it can be converted into a body. And the conversion to a body will actually remove that layer and will forward it into the body, because then we'll have done the second half of the implicit representation workflow, which is the conversion of an ISO surface into a 3D geobody. So this geobody, once it is converted, once you don't see it anymore under the volume, but you see it here, is not anymore linked to the input volume. So it has the same property as the previous one, and these geobodies are nothing else than a very complex set of triangles. These objects, they don't have positions. They are only positions in terms of number of triangles and vertices and so on. But they have no x, y, z values, so to speak, that we can use and compare with a surface, for instance. So this is how to create a geobody with implicit representation. And as soon as you change the ISO surface, you can trim out the data and leave out only the brightest and largest bodies. Nevertheless, with this method, you are very likely to generate a lot of very small, very tiny, and most often insignificant bodies. In order to overcome this, there is a new module called Voxel connectivity filter, and that is how you can compute connected geobodies. That is to be found in the volume builder element, that is this icon in OpendTect. It is part of the volume builder module of OpendTect. So you see the step called Voxel connectivity filter. This part of the volume builder module, which is actually a standalone plugin sponsored by Tetrale, is doing pretty much the same work as what we have done previously. So it is taking one volume as input amplitude provider, and we'll use the very same volume that contains the instantaneous amplitude in a given interval. So this was a step of a kind stored volume that must be done prior to using the Voxel connectivity filter, because it provides the input for the filter. Now the Voxel connectivity filter will also compute the position, so the envelope of the limit between large amplitudes and low amplitudes with respect to a cutoff value, but it will also classify the two areas into what will become the output body and what will be the outer part of the body. And then you can choose that the output body should be the amplitudes less than the threshold. And that would be if you would have, for instance, a similarity and you would try to locate low similarity values, you could use a value less than. But we are working with high energies and we are trying to locate the high energies, so we'll set this option to values more than. In that case, the output body will be the envelope of all the high amplitudes with a limit set down to 5,000. There are two other modes. You can also put a value within a given range. That would be if you would have, for instance, an inverted acoustic impedance volume. You could use this, a broadband impedance volume. You can also use the values outside, and that would more work if you would have data like seismic data, and you would try to classify the large amplitudes regardless of their sign. And that would also work if you would have a colored inverted volume, so a seismic data set inverted into relative impedance, and you would look for the largest impedances regardless of the polarity of the impedance change. But in our case, we'll set the filter to values more than 5,000, for instance, and the connectivity will need to be defined in the directions that are allowed to assess the connectivity between two consecutive samples. So if two consecutive samples have both a value above 5,000, then we will have interconnected samples. And the interconnection can be by the common faces, by the common edges, or using both. So using the full 26 neighbors for each sample, for each voxel in the volume. You can also use the option to keep bodies, to only keep bodies larger than a given number of voxels. And I recall that one voxel is one sample on the 3D grid. And this option is what we need to use in order to trim out all the very small, insignificant and isolated bodies. Finally, one of the last things we need to decide is what kind of amplitude to output. We can set the output to transparent if we want the output volume, because this volume builder will create first a 3D volume before creating a geo-body. We can set this to transparent if we want this 3D volume to contain the input amplitudes that are the instantaneous amplitudes. Or we can decide to output other features that are not available with the standard implicit representation, and these are namely the body size rank, which will be from 0 to as much bodies as we have, with 0 being the largest volume, 1 being the second largest, and so forth, so by decreasing size. And we can also output the body size itself in number of voxels. And the body size, since it is a number of voxels, can easily be used to convert and it can easily be converted into a volumetric estimate by multiplying simply by the bin size and the vertical sampling rate of the seismic data. This would be, for instance, this would output the body size in high energy areas. That is what this whole setup would do. That is for the voxel. That's the name of the step for the voxel connectivity filter. Actually, one needs to specify a name for this entire setup. So all the steps that will be done one after the other. And once this is done, don't want to overwrite it. Once this is done, we can press the button OK. That will bring us to the batch processing window of the volume builder. And in here, there are two things we need to do. We need to provide an output name for the output volume, and we need to decide very carefully the volume subselection. You have to remember that the volume builder is very different from the attributes engine, because the volume builder does all the computations in memory in a full 3D manner. So it doesn't work inline by inline or trace by trace. The computations are done in one go for the whole volume. And the volume builder, the volume subselection must be set in such a way that we will provide here the output size of the volume we wish to receive. And that can be completely independent of any input data that will be used, and the volume builder can even run without any input data. And as a result, we can also choose any other bin size, so it doesn't need to be exactly the actual seismic bin size. It can be coarser. And once the volume selection has been set and we have an output cube name, then we can proceed and launch the batch computation of this Voxel connectivity filter. Once the Voxel connectivity filter has provided a volume, this volume can be visualized in the volume rendering, just like any other volume we have had before. Okay. So this is showing us interconnected bodies that have at least a size of 500 voxels. And in this first example, I have output the energy of the input attribute, the energy of the seismic data, instantaneous amplitude. I have also output the other possible outputs of the Voxel connectivity filter. So this is the size and the rank. So the rank, as I said, ranges from 0. So this one is the largest volume, the largest body from all the cube that has been created, and you see with the amplitudes the increasing rank of these geobodies. Okay. So one color is one different isolated body. And then you can assess their size by outputting the size quantity, and the size will be this number, this amplitude here that you see on the color bar and in the status bar is the number of voxels in this geobody. And if you multiply this number by the bin size, so 25 meters by 25 meters, and by the sampling rate that you have to convert to meters, so 1, then you can get an estimate of this volume, of the used volume in cubic meters in this example. So this is how to use the Voxel connectivity filter. In a sense, it works in the very same way as the implicit representation. Sorry, the way to create geobodies from the Voxel connectivity filter is pretty much simple. Is pretty much the same for the second part, but differs in how the input volume is created. So we are not using one single attribute as input here when loading it in the volume, but we are also trimming it a lot before actually adding the isosurface and converting the isosurface into a geobody. And that would be, for instance, a converted geobody from this Voxel connectivity filter output in the volume renderer. Finally, the last kind of geobody I would like to present in this webinar is connected geobodies that were computed in a very similar way, also by assessing the interconnectivity between the samples and by looking at the amplitudes of a given attribute. But the main difference is that we'll use multiple volumes in order to reach this goal and to create the volume used to derive the geobodies. And this is a utility you'll find in the MPSI volumetrics. How does it work? If I go back here, it works from the analysis menu. We'll go to the MPSI utilities and use the module volumetrics. And this Voxel volumetrics and connectivity module, I have saved setup that I'll restore now, is, as I said, using not one single attribute for the input computation, but using multiple components volumes. And this tool was initially designed to work with stochastic impedance realizations. So the output of a stochastic inversion in which you would have in one volume up to 100 impedance volumes that are different realizations of the plausible subsurface impedances. And we can select any number of realizations. And in this webinar, I'll not use an impedance volume, but I'll use something that is closer to my instantaneous amplitude. I'll use a spectral decomposition output at 3 given frequencies. The frequencies were derived in the attributed at 25 Hz, 45 Hz, and 60 Hz. So that is the component 1, 2, and 3 respectively. The processing is also limited by a top and a base horizon, and one can even make a subselection by using a subtraction surface. The connectivity mode is pretty much the same, either common faces or faces and edges or faces, edges and corners. And you can also make a volume subselection. The output will be also a connectivity volume, which is very similar to this rank volume. But you'll also, and you'll get such a connectivity volume, you'll get one for each independent realization, and you'll get a probability, which will be the probability that all the realizations or n number of realizations are interconnected at a given bin ID. Because you have to imagine that if you have multiple realizations, you'll have n times a set of geobodies. And for instance, in one realization, this body could extend up to here, but in the other realization, it would be missing from this position. And that is why you also get a probability volume in this volumetrics and connectivity as an output to the volumetrics and connectivity module. A second major difference is that the Voxel connectivity filter will try to create and to extract all the possible bodies in a 3D volume given by the volume subselection. In the MPSI volumetrics module, we are a bit more specific because we'll only try to get the body of a number of user-defined positions, user-defined seeds that are either coming from wells or user-defined, and that is one in-line, a cross-line, and a time position. That is one point, one peak position in the 3D space. And in order to avoid getting some too much noise, we can delete the size of this point in order to make sure that we'll at least be able to start and to seed the creation of the 3D body. The amplitude specification is pretty much the same. You have to define a cutoff in amplitudes in order to extract your geobody, and that it must be a minimum and a maximum value. So, for instance, in this example, since we are looking for large amplitudes, we may want to choose the same minimum, but we'll use a very large maximum value. Once everything is specified, you can save the settings and press process. This processing is a bit slower than the Voxel connectivity filter because it has to work on many realizations, and we have to generate not only one connectivity volume, but multiple connectivity volumes and one probability volume. The output is rather similar and can be converted afterwards into a geobody, once again using the same tool. So by loading the output volume in a volume viewer, by adding an isosurface and converting the isosurface into a geobody. And then you get, for instance here, this is the probability that, the geobody corresponding to a probability larger than 50% that we have interconnectivities in the realizations. So 50% means that there is actually connectivity in at least one of the 3 spectral decomposition attributes. well, sorry, actually in two out of 3. And if I lower the cutoff down to 0.25, then this is the probability that we have at least 2 interconnected bodies. Okay. So these are various kinds of geobodies that you can see and that you can extract from OpendTect from the fully manually picked versions, so the convex bodies, to the polygon-based bodies that follow the structure that use top and base horizons. And then you go to the next family of geobodies, the ones that are extracted from volumes using either a raw attribute or the Voxel connectivity filter in addition to this to one given attribute, or the MPSI connectivity and volumetrics module in combination with a multiple component volume. So either a spectral decomposition or a stochastic impedance inversion output. Now, if I summarize what we need in order to do any kind of interpretation, geobody interpretation in OpendTect, you always need to do some kind of a priori interpretation, and that can be done pretty much with OpendTect alone. You can do a whole lot of things in OpendTect. You will find default attributes that can be used. You can apply your attributes on sections, on horizons, between horizons, and so forth. And the spectral decomposition is one of the main attributes you may want to use when starting to interpret your seismic data, but also the similarity. And if you use one of our commercial plugins, like colored inversion, deep steering, horizon cube neural networks, so that was the waveform segmentation and SSIS, then you can go a bit further into your interpretation and create additional attributes that can guide you a bit further into your interpretation. And that is for the a priori interpretation. When it comes to the body type, in order to pick manual convex bodies, you only need OpendTect. The speed is largely dependent on how chaotic your feature is in the attribute you are using for the picking, and that is because the interpretation has to be done fully manually. When you use polygons and horizons instead of full manual picking, you will need the additional SSIS plugin. So this kind of geobody created from a polygon and 2 horizons is part of the SSIS plugin. And but it is a good add-on because it since you only need to do a lateral manual interpretation, the time you'll spend in interpreting the geobody will be reduced by quite a large amount. And also, because it is based on a 2D polygon, you'll have all the freedom to get a very large lateral complexity in your polygon and subsequent geobody. If you want to do implicit representation, so every time you are loading a volume in a volume renderer in the tree, creating an isosurface and converting the isosurface to a body, for this workflow you only need OpendTect. The computation type is rather fast most often because the amplitudes of the volume have been loaded in memory prior to the creation of the isosurface, so it's pretty quick. But it can vary with the complexity of the geobody and with the amount of variance, lateral variance you have in the input attribute, in the input volume. The export that I'll present after this slide is only I would say the inverse of the implicit representation. It consists of taking one body and converting it to a volume. We'll see this after this slide, and as such it doesn't require more than OpendTect because it's only the inverse process as what we call implicit representation. The Voxel connectivity filter is a plugin to OpendTect, a free plugin whose development has been sponsored by Tetrale, and it is a bit slower than the implicit representation because we have to process the volume in 3D, in full 3D mode, and we have to assess the interconnectivity of the bodies. So it is a two-pass process that is a bit slower than the implicit representation. Once again, the speed really is more proportional to the amount of complexity and the amount of variance you have in input volume. The MPSI connectivity requires, hence the name, the MPSI plugin, the stochastic inversion plugin of the MPSI suite, and the computation type once again depends on the volume size and complexity, but is in general, and that's why I've marked it as a minus for the speed, it is in general slower than the previous two, and that is only because it has to work with a larger number of data, and it simply takes more time to manage all this data. Nevertheless, it is a bit slower, but you may have more ways to impact on the results because you can set yourself the position of the input seed, and you can also use more relevant attributes because you are using a whole set of realizations instead of one single attribute. Let me finish this presentation by showing you how to export a geobody. So assuming you have created a geobody like this one, you may want to export it into another software. The export is to be done in the volume builder because the volume builder has a step called body shape painter. And this body shape painter has a very simple task. It will take one of these bodies as input and put one constant value in the body and optionally one other constant value outside the body. And that will be a very simple rule that can be used to output. So this step, once computed, will output the value 1 in a given body. If you want to output several bodies at the same time, and if they are not overlapping, you may create a flow and select multiple bodies and put here I would put another value in this second body. So then these will be two steps, and you have to remember that the steps will be taken consecutively, which means that if there is only overlap, the last step will always overwrite at a given sample the output of the previous steps. The creation itself is very standard. You have to provide an output name for the volume builder setup. You press on OK, and that will bring you to the batch processing window of the volume builder, in which you can choose the volume subselection. So you may want to restrict the ranges or the bin size, or you may want to increase the bin size of the output volume, and you would output it in a new volume that could be called exported bodies. And by pressing proceed, you would launch the batch processing. Once you have this, you'll see the exported volume in the seismics management. And as for any 3D volume, you can then, because it is a 3D volume, export it either in SegWi format or in simple text or binary files, or you can use any of the Petrel or Workstation access links you have if applicable. So the export is pretty much straightforward. So this last step, the export of geobodies, concludes my presentation on how to interpret geobodies in OpendTect. And I hope the presentation has been very clear. If you have any questions regarding to this webinar, you can always contact us by going on our website in the contact part of our website, and here you'll find all our phone numbers, but also the email address you may use if you have any further questions to this webinar or in general. So I would like to thank you for your attention in this webinar, and I hope to see you back again in next month's webinar that will be focusing on the chimney interpretation using OpendTect and the neural network plugins. Thank you. Goodbye.
Thanks for a very beautiful presentation. Actually, I'm a new user of OpendTect. I'm basically using Landmark software. I am a geoscientist in ONGC India. So actually, can you guide me something so that I can start with in your software? Like I have gone through your website. So there are multiple volumes and I'm very confused which of the how to start with as a beginner, because Voxel, Geo and these are very good tools, but to start with in OpendTect, can you suggest me which data bank I should download and practice it?
Yes, this was a general question. I would say that on our website, actually not on the DGB-ES website, but on the OpendTect website, you know that we have an open source seismic repository.
Yes.
That is available. So if you
if you can show, that will be very good.
OpendTect seismic repository, and this allows you to download a number of surveys that can get you started with working in OpendTect.
Okay.
And the very first thing you want to do when you are in a brand new survey is you want to very quickly screen through attributes, and in order to do this, if you open the attribute set window, you'll see this icon here, and this icon shows you a number of attribute sets you can load, and that will help you getting started in OpendTect. So for instance, the evaluate attribute set is giving you a number of attributes ready to be applied on your data set, and that will give you a quick overview of what is happening. And these attributes, I recommend you to apply them on a number of sections of your data set, but also on horizons in a very same way as I have done in the beginning of this webinar. So don't be afraid on really applying lots of attributes on various interpretations to get a feeling of what is happening on your data set. And once you see that some anomalies remain visible and are correlated between different attributes, then you may want to try to begin isolating these anomalies using more complex tools like geobodies or other tools, or polygonal subselections and so forth. But the basic steps are really to take the time to do the attribute analysis, to go through the data and do the interpretation.
Okay, thanks, Huck.
You're welcome.
Go ahead with your question, Shafiq. Shafiq Ahmed, you can go ahead with your question.
Excuse me, can I ask one question?
Yes,
Yes,
please.
go ahead, Valentina.
Actually, I'm working in a limestone regime. Okay, so
Yes.
for one particular age, I have seen that there are phases changes from clastic to limestone.
Yes.
So can this voxel geo help me in identifying those that phases boundary and some depositional thing?
It will certainly help you in contouring the anomalies. In order to, and that is really by creating these kind of objects. So
Okay.
by if you input your input attribute to a volume and then convert it into an ISO surface, then you'll certainly be in a position of being able to contour your attribute response. Then the
Because
second part, the identification of what these bodies actually mean, will still need to be done and will actually be your interpretation. But
because what is the basic difference is from clasting to limestone, I'm seeing the drastic amplitude change.
yes,
And at the certain area, the clastic, which is representing high amplitude, some few areas are very strong in amplitude. So
yes. We cannot hear you anymore. Well, I will try to answer. Yeah, I would say that this ISO surface tool works really greatly as soon as you have a very quick change in amplitude of the input attribute. And that was the case with this horizon here, where the change of amplitudes here between the blue, where the amplitude is around, that's something you can see in the status bar, is close to 8,000, 7,000, 8,000, goes very quickly down to 1/3, 1/4 of this amount. And if you have such an attribute, then you can very efficiently set the limit to this well, more or less between these two areas, because you have a very sudden drop of amplitudes from one part of the area to the other. So as soon as you have such an attribute, like this one, instantaneous amplitude, you can be quite sure that it will be easy to convert it into a geobody. And then the trimming using the voxel connectivity filter is also rather easy, because you will have set the threshold already. It is the same value. It's very likely that you will use the same value here as what you have used when creating the other surface. And the trimming is very easy to test, because you'll quickly be able to apply this voxel connectivity filter a number of times in order to filter out the small bodies and to leave in only the large interconnected bodies.
Okay, Aizer, go ahead with your question.
This is Azar. I work with OpendTect in Canada portion. So just to answer some of the question for ONGC, because I have used Voxel Geo in the past, so I understand what you're trying to understand in this. The workflows are different, especially I'm just answering the one question from ONGC, that you might want to use for the specific between carbonate and sandstone to be used spectral decomposition, which is in the base version. Because in the plugin version you have what is called the UVQ, which is facies analysis, which can differentiate quite good between the various carbonates versus sandstone. But just in the base version, spectral decomposition probably would provide you a better over an interval. So interval-based analysis could help a little bit more before going into the geo-body detection, because the amplitudes, yes, amplitude response might be different, but they may not be fully separable on the basis of just the amplitude. So it means in different frequencies they may have a better dominant amplitude. So using like this 3-color red, green, blue, like RGB spectrum, and the workflows, all of these workflows are in the base documentation. There is a whole documentation to show the workflow, which you can self-learning, and I think Arnaud can point you to the right place where the documentation is downloadable, including the data.
The workflows are always available here. Once you have installed the software, you can simply press the F3 key on your keyboard, and that will bring you to the workflows documentation. And here we are listing a number of workflows you can run in OpendTect to get very quickly started. And one of them, as you said, is spectral decomposition. That is really listing you all the steps you have to do in order to perform a spectral decomposition. Okay, and all that help documentation is available inside the OpendTect installation folder. You can also go to our website dgbes.com and go not to the contact part but to the support part. And here you see you'll find a user documentation, but also a number of tutorials that are of great help for new beginners. You have a self-study OpendTect course you can download, a manual, full manual filled with exercises. You have a number of tutorial videos and how-to manuals. And for instance, there is a very specific how-to manual on color stacking and RGB blending in OpendTect.
Any more questions? Okay, I think thank you very much, Arnaud, for the great presentation. Can you hear me now? If anybody has any more questions, you can just write it down. We'll give 1 second more if you have any question. Okay. Please feel free to email us anytime at webinar@dgbes.com if you have more questions. And we have a webinar every month, so you feel free to register next month with us, and we'll be glad to see every one of you just joining us next month. And we'll also be receiving a link with all the recording session for today. And it will be in our Facebook and in LinkedIn page. Thanks, everybody, and see you next month. Thanks, Arnaud.
Thank you, Venice. Goodbye.
Goodbye.